Let's start with the official part now. And first of all, I would like to wish you a good morning, or maybe good afternoon, or good evening, depending on where you are. All the speakers, all the delegates, all the participants on the global webinar on material science and engineering. And I think this is the 5th time we are having this interesting conference. Yes, my name is Dr. Per Löthman. As just mentioned, I'm from Hamburg in Germany, and I'm the chairperson of this conference. And I am also, in my spare time, so to speak, I'm a CSO at the Chief Scientific Officer at the company Foviatech GmbH in Hamburg, in Germany, and they're also affiliated with some universities, the University of Kaiserslautern and Berlin, as well as Hamburg, where I teach and do research. First of all, I would like to, on behalf of the organizing committee, it gives me, of course, indeed, a very great pleasure to welcome you to our meeting. This is the 5th global webinar on material science and engineering, organized by the Global Scientific Guild. Thank you all for coming and attending to this that we can have this opportunity to get together simply because of the online opportunity, right? It's so easy to get together just because even though we are at different continents, we can get together and talk about research. Today, it is an important event, of course, which is initiated by the Global Scientific Guild. It will provide opportunity to share research as well as encourage each other to set up new collaborations, as well as address challenges, overarching challenges and interdisciplinary challenges related to material science and engineering. We are very pleased to welcome you to both share and witness the advances in this field together. We have speakers from all over the world. I think almost all continents are represented this time. And as I said, I am happy to share this intense period of discussion, collaborations, and generation, and to generate innovative solutions to address the challenges that still exist in material science and engineering. And I'm happy that this conference has continued to attract speakers and delegates from all over the world. And I would like to thank all the speakers as well as partners for their continuous support and patronage. The Global Scientific Guild also wishes to thank all the organizing committee members who have put in long hours and generated many creative ideas to bring this meeting together. Finally, we would also like to thank each one of you, all the participants of this conference. We hope that you will enjoy the conference and that your participation will lead to new creative initiatives. Please enjoy the conference, and please also help us to improve future conference with your open input, if you so wish. I am looking forward to a very interesting and exciting conference. Thank you. Okay. And I also hope that you can hear me, what I'm saying. Otherwise,
it's fine.
Okay, so let's see what we can do here. I have this time I'm going to talk about heart, livers, and hydrogels, improving biofunction via 3D bioprinting of cell hydrogels, and that is a very, actually, to be honest, it's a quite hot topic, if I may say so. And what has this, maybe you ask yourself, is this really material science? And I think it is, and we will see why this is material science. Hydrogels that are filled with cells, so to speak, is very exciting, as well as challenging material itself. Before I go into the details, maybe I could very briefly just say, why on earth do we do this, right? 3D bioprinting, what does it mean? Well, ultimately it means to be able to print organs, ultimately functioning organs, right? Such as hearts or livers, by using hydrogels. And why is that important? It is important because there's a lack of transplantable organs worldwide. So a number of patients die every week because of the lack of transplantable organs. So it is an important topic. First of all, I would like to thank my collaborators at the University of Saarland, as University of Twente, as well as KISS Europe, and Kaiserslautern is actually missing here, but that's why I mentioned it. So this is how a bioprinter looks like. Let me just briefly introduce what I'm going to talk about and the problem formulation in a way. The encapsulation of cells within a gel phase materials to form bioinks. Bioinks is what we use in a bioprinter, just as you use any other ink in other 3D printers, right? And hydrogels offer advantages for the next generation of 3D printing. It is a promising tool for patterning cells, but the technology itself is is of course not mature enough, because it has some issues because of the lack of suitable materials for the bioinks. Normally you use viscous polymers, but those are not always biocompatible, which means that the cells that has to be present in the bioink will simply not be viable. They will simply not be alive anymore. So current challenges and opportunities that arise here is that bioprinted constructs, they are related to the fact that bioprinted constructs are living composites in a way, right? So hydrogels, since they are contains a lot of water, as well as they can come up with a robust network of polymers, it is believed that the hydrogels, including their rheological properties, will be a promising alternative for bioinks. And engineering hydrogels with consideration of cells as an intrinsic component of the bioink will, I hope, enable control of the evolution of the printed construct, of the living construct, and that we ultimately will get to the goal, which is greater biofunctionality, and at the very end, a transplantable organ, be it liver or heart or kidney or skin, for example, right? So let's go into the basics a little bit. Native tissues are living composites of cells embedded within a complex extracellular matrix. So that is also very close to how hydrogels work. As a class of materials, hydrogels can be considered as uniquely suited for applications in 3D bioprinting, because they provide polymeric, they may contain polymeric components, and they provide, therefore, mechanical protection, as well as thereby structural support during the printing process. And they can be tuned, and they can mimic many features of the ECM to be customized to influence cell-gel interaction, also post-printing. What do I mean by this? They mimic features of the native ACM. ECM is the extracellular matrix, and that is basically what we need, right? We put cells into an ink, and we need an environment which is similar to the environment that the cells experience in the human body, and that's the extracellular matrix. And we are talking about not only the printing process itself, but also about post-printing, what is happening. We are talking about living cells, so there is a maturation of the printed organ after printing. So, and yes, a little bit more of the basics. I hope I'm not too fast. I have maybe even I have quite a few slides. I hope I will be able to explain this properly. So 3D bioprinting comes from 3D printing, and the difference is, of course, we are dealing with a bioink, and they have to meet some different kinds of requirements compared to normal 3D printing, and that is the physiological cell volume fractions. Now, it's very easy in a way if you consider how can I print an organ, be it a heart or be it a liver. You have to think about this. What is the physiological cell volume fractions in the organ itself? In cartilage, it's around 1 to 2%, and around 80% in liver and 90% in muscle. And I think in heart, it is similar, 80 or 90%, maybe even over 90%. So if I look back very briefly, in the beginning of 3D printing, we have been using thermoplastics or scaffolds with to print complex structures, and these are of course functioning, but they are not so biological compatible, and they do not mimic native tissues, as I was mentioning before, the extracellular matrix, you remember. And so hydrogels are believed to encapsulate larger volume fractions of cells, and therefore they are suitable for these things. And yeah, so what is this? This is just a sort of definition. Bioink for 3D bioprinting on composite mixture of polymeric material and living cells that is deposited and solidified into a pre-specified geometry. That is the definition. This geometry can, for example, be a heart. Hydrogels are water-soluble, insoluble polymer networks formed through chemical or physical cross-linkage. That's very simple in a way, but what it means, what is even more important here is actually water swollen, right? It contains a lot of water, exactly those things that a cell will need. And you can also in hydrogels incorporate other things that that are important for the maturation of the organ after printing. Well, we'll get into that a little bit more in detail later. What I'm talking about is enzymes, for example, that could possibly degrade the polymer network, which is not necessary, right? And also growth factors and other biological cues that are important for the function of the organ. Now, so challenges in fabricating constructs that replicate both the structural complexity and biological functionality of native tissues. That goes without saying. This is a general challenge that we have. So when it comes to the bioinks, we also have the remaining challenge of biomaterial support. It's not only rheological properties that are important here, but also support of the cells at all stages of printing. Why is this so important? Let me explain this very quickly. Cells must survive, and if they die, there is no use of printing them, right? And I will get into that later. What are the risks for that cells are dead basically after printing? Well, let's take the nozzle of the 3D printer, which can exhibit shear forces that can rupture the cell membrane. That's just one example. So here we have, that's actually number one, the challenges while suspended in the syringe, right? It can also be, for example, we need a certain property of the bioink in order to prevent sedimentation. And during extrusion through the nozzle, that's what I just mentioned, right? The shear forces and the flow profile may rupture cell membranes during any material cross-linking step. Cross-linking is something we sometimes need post-printing in order to make the printed construct stable. We might want to cross-link the polymers that are contained in the heart or liver, right? As the final construct matures to become more tissue-like after printing. Those are challenges that we all face in general. Most tissues in our body are active hydrogels. That is true. So all bioinks are dynamic living materials, as well as most tissues in our body are active hydrogels composed of non-living polymers and living cells. And in a way, we would like to mimic that by using hydrogels. And so they are hydrogels, as I said, are attractive materials to combine with cells for use as bioinks in 3D printing, since they are mechanically and biochemical. They can mechanically and biochemically support the cells during and after the process. That is to say, they can protect the cells from shear forces, etc. And also they can provide the mechanical stability of the printed construct. Now I have to go into this a little bit. This is maybe a little bit too much. When we talk about hydrogels, we can also compare with sol phase inks, right? Those are another class of inks. Now, the key advantage of using hydrogels in bioinks is that they shield cells from mechanical stress during extrusion and preventing cell death and any unintended cell phenotype changes. If we compare with sol phase ink, it is basically like this, that we have, what did I want to say? We have the sol phase is actually has a very different viscosity, and viscosity is actually crucial to cell survival. Those shear stresses, if we have let me just excuse me, I'm just lost track for a second here. It is actually like this, that the sol phase bioinks, they exhibit a much lower viscosity, and therefore the cells are more, so to speak, experience higher cell shear stresses, which are directly damaging as well. And what does it mean? It's not only that we can break the cell membrane, but also to affect the cell morphology itself and the cytoskeletal organization. But not only that, gene and protein expressions are also affected with this, and also the biological functionality. Now, in many gel phase bioinks, we can have shear thinning, which means that the viscosity will go down a little bit as we apply shear forces, but then it acts also as a lubricating layer, allowing the rest of the gel to pass through the extruder. So yes, this is, if we take this one step further to think about this a little bit, how can we improve this, and what are some material requirements for gel phase bioinks? This is actually much more complicated. I almost say it's a lot to say about this, and I cannot go into all the details, but we are talking about yield stress, viscosity, shear thinning, self-healing, support materials, biochemical processes. Each one of those expressions here deserve its own talk, actually, but just let me mention a couple of comments here. Yield stress, it represents a stress for a gel to begin to flow, and also we need a certain viscosity as well as yield stress, also to prevent cell sedimentation, and we need a sharp decrease in the viscosity in order to make the bioink printable. Now, there's a fine balance. If the yield point is too high, we might need very large pressures, and we cannot always achieve that. And this itself can also lead to cell death, right? The viscosity is a measure of the resistance to flow. That's a general statement, and we know that. Yeah, so it influences the bioink's ability to be extruded, and it plays a role in print fidelity. Higher viscosity impede droplet formation, which is important. We need to print with a continuous filament since the printing itself is layer by layer. So high viscosity inks are preferred, and also in terms of resolution and shape retention after printing. So, however, if the viscosity is too high, the print needle might be resistant to flow, leading to an inconsistent deposition. So there is a balance here. Shear thinning is a good thing because the viscosity decreases with the shear rate, and that is also something that we need. Self-healing defines as a material's recovery after an applied shear stress is removed. I don't have to say so much about that. That is something we would like to have. Then support materials, what is meant here is that, for example, fibrous materials can be added to an ink simply because they can align and pass through the nozzle, as well as support the material after printing. The biochemical properties that we would need is we would need, for example, signal molecules that can provide biochemical signals after printing. And we can, it's also important because of cell communication after printing. It depends on the cells, of course, that is used, but we are talking about growth factors as well as different kinds of ligands. We are also talking about enzymes, for example, that can be excreted after a while post-printing to degrade the, at that point of time, polymer support materials that is then not needed. Yeah, so what do we have here? This is just, yeah, it's basically what I already said. You can have a look at it. It's what do we need for the yield stress, homogeneous cell distribution. And we don't need, I'm looking at the left now, we don't need cell sedimentation, shear thinning. What is we want is plug flow and not extensional flow. I forgot to mention that plug flow is something that we have with the gel material, hydrogel material, but not with the sol material. This plug flow will prevent shear stresses from becoming dangerous, so to speak, since we have a lubricating layer. Viscosity will, high viscosity will make a stable filament, as you can see here to the left below, and it will prevent droplet breakup. So then we also have another I'm probably running out of time. No, I don't know, but let's hurry up. Let's only have a quick look at this slide, maybe. Cross-linking strategy for dual stage inks. What I mean by this, what is dual stage inks? The dual stage inks are basically first stage cross-linking and second stage cross-linking, as you can see here. What it means is basically the cross-linking that can be done prior to printing, and the second stage is the cross-linking that can be made accomplished after printing, and that can be so to speak, induced via light or high ion concentration. Enzymes and small molecules and so on and so forth can support this. And you see, there are two things that we need for the bioink. It must be printable, but it also has to provide, contain components that make the construct, the printed organ, stable post-printing. So here is one example here. This is hyaluronic acid modified with adamantane beta cyclohydroxydextrin, and this is a dual stage cross-linked bioprinted structures. After shear thinning and self-healing, what we see here is a shear thinning and self-healing bioink based on supramolecular self-assembly through guest host complexes. In this case, it allows for continuous printing in any direction of 3D space and seeding also with endothelial cells. Yes, this is actually, yeah, as I said, hyaluronic acid was modified with adamantane or beta cyclodextrin and mixed for this. And in this particular case, the mechanical properties of the bioink could be modulated by varying degree of chemical modification. In other words, hyaluronic acid. Hyaluronic acid, for those of you who don't know this component, it's something that we have in your eyes that makes them wet and, well, like a hydrogel, basically. So here are some filaments printed with this structure. Yes, again, this is also a dual cross-linked tyramine modified methyl cellulose 3D printed lattices, and it also retained the structural stability up to 60 days, while in this case they did not, those who did not undergo a second stage cross-linking did deteriorate much faster. Here in this picture, you see printing with gelatine as well as fibrinogen. It's a dual stage cross-linked pegylated gelatin in red and pegylated fibrinogen in blue. Those inks were printed together and then covalently cross-linked via small molecules. And this is a multi-cell type printing. Two types of cell, HMSCS as well as UVEX, could be used in this case. So that is also exciting. Here we have another experiment, example of a polymerizable shear thinning pluronic hydrogel ink, which was mixed with a initiator persulfate. It was printed upon a supporting catalyst, as you can see here in the middle. After removal from the bath, that's the lower, the pictures below, number D and E, a complex printed structures such as an inverted cone, that's the picture D and E, retain their shape without collapsing. And this is much due to the polymerizable shear thinning pluronic dimethacrylate. Again, I will move on to the next part, which is basically post-printing effects or complex tissue types. Post-printing effects what are they? They are the interaction between the cells and the matrix, and between the matrix and the cells. In general, post-printing, the living construct will change and mature over time. It can be influenced by the material design choices, of course. Bioprinted constructs are dynamic hydrogels, and they will evolve over time as the polymer components interact with the cellular components. So what we need here is, in the future, we need to develop customizable bioink polymers that can guide the polymer cell interaction, and also include excuse me, there's one more thing that I wanted to say. The embedded cell can act on the polymers through cell-generated forces, and matrix remodeling, and degradation can be a cause of this. So it's not only the polymers and the printing process, but the growing cells themselves can also act on the polymeric scaffold, so to speak. We can use as you can see here, external stimuli at the bottom in order to freeze in this situation in a way, such as electrical stimulation or mechanical stimulation, or photo patterning in order to accelerate the maturation into maturation, meaning in this case, of course, more tissue-like constructs. So I mentioned cell-generated forces or focal adhesions, the cell-generated forces that we can see here. I believe that I'm running out of time, so I will take this just briefly. What we are talking about is, as you can see in the two pictures below here, cells, they work with focal points, right, or focal adhesion points, which with which the cells attach to any surface, basically, and they exert forces. And during cell growth, post-printing, they can not only, those forces can be so big that they change the geometry of what you want to print. And that is what you see here below in the two pictures. This is actually quite interesting way of seeing it, right? This was supposed to the left below be a nice propeller, and it deformed into something else. The same thing goes for the picture to the right below. This nice propeller had crumbled wings at the end, right, due to cellular forces via focal adhesion points. So in other cases, we have this is more of a buckling of microbeams, which could also be cell-generated contractile forces cause the undulation of those printed microbeams made of collagen in this case. Here we have another example. Here, this is a printing of 3 different kinds of cell types. They are marked here in red, blue, and green, and it's simply just a demonstration of 3 different cell types at one time. That is to say, we have 3 cell types in one hydrogel bioink. In this case, fibroblasts, HNDFs, HUVECs, and this is an example for that they retain their spatial identity over at least 7 days. This again, multiple cell types may be encapsulated within a single bioink. The properties of the hydrogel materials may be so engineered to form geometrical complex structures and cell patterns. Here we see multiple cell types, HMCS, green, and UVEX, red, and maybe encapsulated in a single bioink and printed into 3D custom-shaped constructs. I am almost at the end, and I would like to come up with some kind of summary by also showing you this table here. Well, in summary, in order to advance achievable complexity of 3D printed constructs for increased biomimicry, that is to say biocompatibility as well as mimicking human organs, the post-printing evolution of and the final, so to speak, properties of the hydrogel-based construct can be governed preferably by the wealth of knowledge from the fields of polymer chemistry, of course, and tissue engineering. Well, as I already told you, we can consider a bioprinted construct as a living composite material with polymer and cells as intrinsic elements. It requires the evolutions of both components to be characterized for a comprehensive understanding of the material. So here, for example, in addition to quantification of the physical as well as mechanical properties, which are indeed very important, of the print over time, also the living component of the 3D printed construct should be assessed with assays, commonly referred to in the tissue engineering community as characterization of cells in gels, and that's what we see here. We can use different kinds of characterization of cells in gels, the viability, proliferation with picogreen, everybody knows that, and metabolism, morphology, confocal microscopy, signaling, immunocytochemistry, gene activation. We can use QRT-PCR, next generation sequencing. Protein expression can be characterized by Western blot. I think a lot of people here have been doing that, I guess, protein secretion via enzyme-linked immunosorbent assay, or as we all know, it's called ELISA. Yes, I hope I have been giving you a little hint about in which direction this future bio-ink and biofabrication might go. So this is basically, I'm talking about pointing out a direction for future development. And I believe sincerely and in the hydrogels, they are the key factor in this. We need to start to understand them more in detail. Thank you for your kind attention. Thank you for listening. Thank you for taking your time. And if you are interested to talk to me outside of the conference, maybe here is my phone number as well as my email addresses. And thank you for your kind attention. Thank you.